So continuing from my last video, you saw that our final answer was this guy up here. And I concluded by saying that basically, if it asked us to represent the function in terms of, a sigma, the limit of a Riemann sum essentially, then we would write it like this. But then my last statement was, hey, well, if it just asks us to write the expression, we do that. But I also said, well, what if we wanted to use this to find the area under a curve? How would we do that? And how we would even do that is by taking the limit of this Riemann sum. And this looks a little confusing, because you see fours, you see i's, you see n's, you see this sigma. And you're looking at all of this and you're thinking, well, where do I even start? And that's why in this video, I'm really going to be doing one example of this, because what you have to know is that limits of Riemann sums take a very, very, very long time and they can be very tedious. So I'm going to be doing one example, but I'll be doing it as thoroughly as possible. But what you're going to need to do in order to, take the limit of Riemann sum and evaluate this so you get the area under a curve is you're going to have to know these formulas over here, especially these three. This one's kind of just common sense, but these three up here, these are these are very important to know. The reason being is that because if you take the sigma of I, then it'll get it in terms of n's. Because you see here, I have a mixture of i's and n's, but I really only want one variable. Because I'm taking a limit as n approaches infinity, not I, so these i's mean nothing to me. So what I have over here are different ways of representing I. So I is equal to n times n plus 1 over 2. I squared is equal to n times n plus 1 times 2n plus 1 over 6. I cubed is equal to n times n plus 1 over 2 squared. Again, these are just formulas to know. I'm not going to really go into the technicalities behind why they are the way they are. It's really just things you have to remember in order to do these Riemann sums. So enough of me blabbering about this. Let's just actually try an example and hopefully it'll start to make some more sense. So again, I'll leave this right here for a sec if you want to take a screenshot of that, whatever, just as long as you remember it and commit it to memory, because that's really the only way you're going to be able to do this. Because if you don't know one of these and you run into it on a test or something, then you could be in a little bit of trouble. So let's just try an example really quickly. Let's just try it, and not really quickly because this will probably take us the whole video. So an example I have is, let's say I'm asked to evaluate this integral by using the Riemann sum, the limit of the Riemann sum. So how would I even start? So it's x squared plus x with respect to x. Well, I first want to get it in this form up here. I want to get it in this sigma form, right? But in order to do that, remember what we did last time. The very conclusion of my last video is we started by saying, well, we definitely need delta x. And this is the same thing. Like, just ignore this part right here and look at this part. That, it's that, and then this is basically running from -2 to 0. It's the same thing. It's just a different way of writing the same thing. So what you always want to do is you always just want to start by computing your delta x. So delta x equals b minus a over n. Well, remember integrals run from, a to b. So this is simply just 0 minus -2 over n, which is simply going to be 2 over n. Okay, and I'm also going to need my xi, just like I did last time. This is like essentially the same thing I finished off with last time. So remember, that's a plus delta x times I. Well, that's just going to be, -2 plus 2I over n, where 2 over n is my delta x, and I'm just multiplying that by I to get 2I over n. Okay, so now let's put this in the form of the limit of a Riemann sum. So I'm going to do the limit. So the limit as n approaches infinity, sigma, and again, the notation is exactly the same. And I is equal to 1, that's my starting value. And now I just have to, remember, wherever I see an x, I plug in this xi over here. So I'm going to get -2 plus 2I over n squared plus negative 2 plus 2I over n. And don't forget to multiply by this delta x. That's a really common mistake I see. So multiply by this delta x, and delta x is simply 2 over n. So again, just so you don't get lost, 10-second recap is that I basically, wherever I saw an x value, wherever I saw an x value right here, I put in the xi. And we established that xi is equal to negative 2 plus 2I over n. So that's all I did. Wherever I saw an x, I put this xi. And then instead of delta x, I put 2 over n. And this dx essentially becomes the delta x, if that makes sense as well. So that's why this delta x is even included in the formula. And again, I'll write the limit of the Riemann sum over here one more time in case it seems like this is coming out of nowhere. But if it is, I encourage you to rewatch my last video, and hopefully then it'll make a little more sense. So remember, it's simply just limit as n approaches infinity, and I equals 1, f of x I star, and then times delta x. So that's just limit of Riemann sum. So again, that's not really important right now. It's really, as long as you know how to implement this, it's fine. So again, just put a delta x here, 2 over n, and then plug in xi wherever I see an x. Okay, so now I just want to clean up the inside of this, because the inside of this sum is looking a little messy. You see that I have negative 2 plus 2i over n squared. So I'm going to FOIL this, the negative 2 plus 2i over n. I really want to make this nicer. So I think off to the side I'm going to do that. I think off to the side I'm going to do it. So negative 2 plus 2i over n times negative 2 plus 2i over n. And again, all I'm doing is this right here. So okay, so this is 4, so negative 2, so minus, so this is minus 8i over n. Again, I'm just foiling this out. And then plus 4i squared over n squared. Okay, so I'm going to get 4 minus 8i over n. Let me rewrite that, it's a little messy. 8i over n plus 4i squared over n squared plus negative 2 plus 2i over n times 2 over n. Okay, and I can see that I'm about to run out of room, so what I'm going to do is I'm just going to simply take this little piece and clear the board. Hopefully this will work pretty nicely. So I'm going to paste this back in. Okay, this is right where I left off, so that works perfectly. So I'm just going to drag this guy back up really quickly, just so I don't lose my progress. Okay, there we go. So now what I have to do is I want to combine like terms within this. So again, oh, I'm sorry, we're supposed to be taking the sigma of this. So let me just clear this right here. So let me plug in that sigma. So the sigma right here, sum, n I equals 1, and the limit. Okay, so what I'm going to want to do is I'm just going to combine like terms within this. So I can do that pretty easily. So this is going to become, so the limit is n approaches infinity. And honestly, one of the most tedious parts about this is you have to keep rewriting the limit and this sigma, which is time consuming in itself. So, okay, so I see a 4 and negative 2, so I'm just going to get 2. Okay, and I see a negative 8i and a 2i, so that's going to give me 6i over n. And I see a 4i squared over n squared, so 4i squared over n squared. And this is still multiplied by 2 over n. So now our last, well, not our last step, but our next step is to just distribute that 2 over n within the sigma. So this is going to multiply here, here, and here. So I'm just going to multiply that to each term within the sigma. So limit is n approaches infinity. Writing this for the 10 trillionth time, but it's okay. So 4 over n minus 12I over n squared. So again, I'm just multiplying these together. So 4 over n minus 12I over n squared plus, so this is plus 8I squared over n cubed. Okay, so before I do that, before I move on though, I want to show you another way I'm going to write this, just to make it a little easier in the future. So I'm going to write this as just 12 over n squared times I, and you're going to see y soon, plus, 8 over n cubed times I squared. Okay, so now the next step is we want to, essentially what I want to do is I see these i's right here, and I see this I and this I squared, and I can't really take the limit yet, and I still have this sigma involved. So what I need to do is I need a way to get rid of that. So let's do this. So what I'm going to do is I'm going to break up this sigma, and that's perfectly fine to do. You can split a sigma up between addition and subtraction. So what I'm going to do is I'm just going to break this up into 3 different sigmas. So sigma right here, so 4 over n minus, and then another one. So n, I equals 1, 12 over n squared times I. And then you're just going to want to do it one more time. So plus 8 over, so whoops, sorry, plus sigma. So n, and then I equals 1. And then 8 over n cubed times I squared. Okay. So now what I want to do is I want to get only those i's and those I squareds alone. Because remember, if you rewind the video, I showed you all those formulas. And if I use those formulas, I can simply just get rid of these i's, and I can also get rid of my sigmas in the process. So I'm just going to rewrite this one more time, and then we won't have to write the sigmas anymore, fortunately. So the limit as n approaches infinity. And I can bring this, this 1 over n out. So what I'm going to do is I'm going to bring this right over here. I can bring this 1 over n out. You can bring your n terms out, but you leave the i's inside because our index is I. We're working with i's as our index. So you're going to leave the i's inside, but here, and you can take the n's out. But here, there was no I in there. We only had a 1 over n or 4 over n. So this 4 is just going to stay there. That 4 is just going to stay there. Okay, and I'm going to do the same thing over here. So I'm going to bring this 12 over n squared out. And this is the reason why I wrote this in front of the I like that, because it's a little easier to see that the I is just going to stay there. It's going to stay inside of the sigma. So I, and then plus, and then 8 over n cubed, and then sigma one more time, last time ever writing this, I squared. Okay. So rewind the video now, because I'm going to be, if you need to, but because I'm going to be using some formulas. So remember that if I have the sigma of a constant, then that's just the constant times n, right? It's just if I had like the sigma of like 1, then that would become 1n. If I have the sigma of c, that becomes cn. So this would become just 4n. And you'll see that these n's will cancel out. Okay, so minus 12 over n squared. And then, well, what is sigma of I? Remember that sigma I, that was simply n times n plus 1 over 2. That worked out nicely. And then plus 8 over n cubed. So then now this is times, well, what was n squared? N squared was simply just n times n plus 1. I'm sorry, I squared times 2n plus 1 over 6. Okay, so now all we have to do is we just have to simplify this and evaluate these limits. And now we're just going back to basic limit problems from the beginning of Calc 1. So okay, so let's just clean this up as best I can. Limit as n approaches infinity. Well, those n's canceled out, so I'm just left with a 4 right here. I'm just left with just a simple 4. And then now you can see that here, and I'll cross this out in red just so it's a little more obvious what I did. One of these n's is going to cancel out, right? So there's going to be an n down below. And this 2 and this 12, that'll just simplify to 6. So that'll simplify to 6. So minus 6. So minus 6 n plus 1 over n. So all I did, 12 divided by 2 was 6, and I just canceled out one of these n's. That's all I did. Okay, so plus, and now what I have to do is one of these n's will cancel out. That 8 over 6 will become 4/3. So I'll read it like that. So plus 4, I'll write it over here. So plus 4/3 times n plus 1 times 2n plus 1 over n squared, because that n squared is still chilling out down there. So okay, we're almost done. I'm just gonna clean this up. I'm gonna simplify this as best I can and just take the limits. Okay, so limit as n approaches infinity. So 4 stays there, and then I'm just gonna distribute this 6. So I'm gonna get minus 6n plus 6 over n. And then over here, this is gonna be, I'm going to do this off to the side. So n plus 1 times 2n plus 1. So I'll write it right here and then I'll erase it. So n plus 1 times 2n plus 1. That's simply going to give me 2n squared plus 3n plus 1. But then remember, I'm multiplying all of this by 4/3. So I'm just going to write it like that. So, okay. So this is plus 4/3 times 2n squared. Again, I'm just cleaning up what was in there by foiling. So 2n squared plus 3n plus 1, still all over n squared. Now my last step is I'm going to distribute this 4/3. So to each one of these right over here. Okay, so last step, last time I'm ever going to have to write this limit. The limit as n approaches infinity. That was a bad infinity. Okay, there we go. Yeah, good enough. Okay, so 4 minus 6n plus 6 over n. 4/3 times 2 is 8/3, so I'm going to get 8/3. And I'll write it like this so it's a little easier to see. 8/3 n squared. 4/3 times 3 is 4, so 4n plus 4/3 over n squared. Okay, so now what's going to happen? Well, you're going to see that essentially, if I take the limit, this will go to 4. So I'm going to 4 down here. This will go to 6. Remember, it's the ratio of the leading coefficients if the degrees on the numerator and denominator are the same. So 4 minus 6, what's going to happen here? Well, this is just going to go to 8/3. So 4 minus 6 plus 8/3. If I compute all of that, and remember, we don't write the limit anymore because we evaluated the limit. So 4 minus 6 plus 8/3, and we're going to get the answer of 2/3. So 2/3, and I'll write that in black, just going to show that it's the final answer. So 2/3 is our final answer. So that was a lot of work, obviously. We had to do a lot of steps. Again, probably it won't take you as long as it took for me. I just really liked showing every single step and how I got there. I know this is a very tedious chapter, or a very tedious section. I didn't like it at all. Fortunately, though, if you're watching this for the first time and you're new to calculus, There's a better way. Trust me, there's shortcuts and it'll make your life a whole lot easier. This method does not stick around forever. So really, well, what is this number right here? Before I close this video out, this number is simply the area of x squared plus x from -2 to 0. That's the area under this curve over this interval, and it's just 2/3. And it happens to be, a pretty clean number. So hopefully you find that a little interesting, that all of this work went into just finding the area under this curve. And again, if you have any questions on this, feel free to message me, or if you have any other requests for videos you want me to do, I'm more than happy to help you out. Thanks for watching.